So in the all the EAS reaction, we have seen that because aromatic compound, they have a substantial amount of high electron density. So aromatic compound generally is capable of donating high electrons toward the electrophile, so make them a reasonable nucleophile. The nucleophilicity obviously depends on exact structure of aromatic compound. Okay. Now, if you have aromatic compound, okay, that has one or more very, very powerful electron withdrawing group attached to it, and that actually can make the aromatic compound electrophile instead of nucleophile because of the electron withdrawing power makes the aromatic ring, the electron hungry. Okay, especially if you have multiple very powerful electron withdrawing group attached to the ring, actually could make the aromatic ring really electron hungry. If aromatic ring becomes electron hungry, then it can act as an electrophile. And especially, if such a compound has a halogen leaving group. And as we learned in organic 1, we know that the halogens, they are generally excellent leaving group, with the exception of fluorine, okay? Because of the halogen, they can take a pair of electrons, the connect to it and leave in the form of a halide. Chloride, bromide, iodide. They are all, the weakly basic excellent leaving group. Okay. So if you have, powerful electron withdrawing group and the halogen leaving group, this kind of aromatic compound can serve as a good electrophiles. So those aromatic compounds can react with strong nucleophiles and give you a nucleophilic aromatic substitution product. So the one of reactions is illustrated here. Okay, so in this aromatic compound, nitro group is the powerful electron withdrawing group. That's the most common electron withdrawing group you will be seeing, most common type. Okay, because as I mentioned earlier, nitro group is one of the most powerful electron withdrawing group I've seen so far. Okay, and then also has a halogen. This is a good leaving group. So the nucleophile is just an alkoxide, and alkoxide, again, the something we learned, the organic 1. If you remember the table of nucleophilicity, alkoxide is the second strongest class of nucleophile. So the nucleophilicity is in the order of about 10 to the 4th. So it's a very powerful nucleophile. So what happens is just the alkoxide, this negative charge part. So hopefully you recall from general chemistry, alkaline cation like sodium, potassium, they are usually just spectator cations, spectator ions. They don't really participate in the reaction. So this sodium methoxide, you can just view it as the supplier of OCH3 minus ion. Okay, just as this one. Okay, the sodium cation just a spectator ion. They don't do anything real. Okay. So what happens is methoxide ion is a true nucleophile and actually replace the chloride. So this whole thing replace chloride and give you the substitution product. Okay. So if you look at the reaction itself, it's just a standard substitution reaction. The nucleophile methoxide replace the chloride ion. So just like the nucleophilic reaction for alkyl halide, but the mechanism is completely different from what we learn in organic 1. So if it's alkyl halide, we know it if, let's say, you know, if alkyl halide react with a nucleophile, I just want you guys refresh a little bit of what you learned in organic one. So the if this one react with become this reaction, what mechanism it is? Methyl bromide react with methoxide ion, give you dimethyl ether. What mechanism of this reaction? This is nucleophilic substitution reaction. Anyone? Can anyone tell me? Chapter 6, organic one. So what mechanism this one is? No one? Let me. Where's the attendance sheet? Do I have the attendance sheet? Okay. I can comment. Oh, you want to answer? Okay, please. SN1. Okay. What is SN1? So SN1 is a involves what kind of key intermediate? Carbocation. Okay. But if SN1 does involve this must come from here, right? It will be a methyl carbocation. So is it reasonable for a methyl carbocation to serve as intermediate? Yes or no? No, because of as we know, the regular carbocation structure varies with degree of substitution. Tertiary is the most stable one. And the secondary is okay. Primary, usually we consider too unstable to form. Methyl even worse. Okay? So this should not involve a carbocation. In addition, carbocation usually carbocation is very acidic species, and this one is a pretty strong base. So if you think about a reaction, it's not very likely for a highly acidic intermediate to form in a highly basic environment, right? And they're not compatible. Just like, okay, I have water. It's highly unlikely for fire to get out of form inside the water, right? It's not absolutely impossible. Highly unlikely, okay? So it's not a SN1. So this is a SN2 process, okay? Because of the, because this one. But anyway, thank you for the, because of the for SN2 process, this electrophilic carbon has a really small steric hindrance, okay? This one of the least has a smallest steric hindrance, can be readily attacked by nucleophile. And a nucleophile always attack from the opposite side of the leaving group. So this is how SN2 works. Okay? SN2 requires the opposite side of leaving group is available for nucleophile to attack. Okay? Now, if you look at this, this reaction. Where's my slides? Okay. This carbon, okay, is electrophilic carbon, okay, and obviously this chloride is a leaving group. So do you think it's possible for the nucleophile to attack from the opposite side of leaving group? So this is a leaving group, right? So the nucleophile can it attack from here? Is that possible? Can nucleophile access the backside of leaving group? Is that possible? Can it come from here to attack it? It can't because it's part of a ring, right? Physically cannot fit in. Okay? So SN2 is impossible. Okay? Now, how about SN1? SN1 means you have to form, the benzyl carbocation. Not benzyl, phenyl carbocation. And the phenyl carbocation, and I believe I did went through the in the the organic one. This kind of carbocation is a very unstable carbocation. Let's see. So the phenyl carbocation, this kind of carbocation, okay, is very unstable carbocation. Is no better than primary carbocation. No better than primary carbocation. Okay, because of the the whatever group you have here, it cannot really stabilize the positive charge. Okay, it's no better than primary carbocation. So it's very unstable. On top of that, if you have a phenyl carbocation, you have a larger, larger angle strength, because if a positive charge on this carbon, okay, this carbon is what hybridization? This is double bond, this is single bond, and no hydrogen on it. So this carbon only has 2 groups of electrons around it. So this carbon is actually sp hybridization. Okay, sp hybridization prefer to have what structure around it? sp. What kind of geometry around it? sp carbon. sp3 is tetrahedral. sp2 is a trigonoplanar. sp is a what? Yes, linear. Okay, linear is 180 degrees, but this one is 120. It's a large angle stress. So benzene phenyl carbocation is very unstable one. So that means SN1 also is very unlikely, because SN1 you need a carbocation. Okay. So that's the reason this guy reaction mechanism neither SN1 nor SN2. So what is the mechanism? We'll talk about later. So before we know the mechanism, let's first look at how the substituent can impact the reaction rate. So if you let all those chlorobenzenes react with sodium methoxide, and all of them has chlorobenzene structure, the difference is just the number of nitro groups on the ring is different. Nitro group is very powerful electron with join group. So if without nitro group, the rate is 1, assume, okay? With 1 nitro group installed at the para side, rate increased by 70 billion times, okay? 70 billion times. So it's a huge, huge improvement, okay? Then if you install another nitro group, now basically you have 1 nitro group para to the chlorine and another nitro group also to it. So compared to the just 1 nitro group, you see the rate increased by how much? Like 30 something thousand times. Okay, and if you have 3 nitro group, 2 of them also to chlorine, 1 of them para to chlorine, and you see the nucleophilic reaction rate is too fast to measure, instant basically. Okay, so what you see is, if you have electron withdrawing group, also or para to the halogen, the more you have, the faster the substitution reaction gonna be. The more you have, the faster it's gonna be. And the meta electron withdrawing group doesn't have much impact on the rate. Doesn't have much. I'm not saying 0. That only have a minor impact on the rate. And that is basically tell you that, okay, electron withdrawing group helps stabilize the the nucleophilic aromatic substitution rate, and especially if you put at the on the position also or para to the halogen leaving group. This is observation. Later we can explain, okay, why that's the case. Now, also, if this is basically a substitution effect, okay. But the other thing we're also interesting to see is if we vary the leaving group, means we vary the type of halogen we have on the ring, and how the reaction rate will change as a result. So in order for us to see the impact of the leaving group, we have to maintain the rest of the structure the same. So we're going to look at all those aromatic compounds with a single nitro group that is parallel to the halogen. Okay? So only thing different among those things is just the type of halogen. Okay? So the interesting what you see is you see that the reaction rate is actually does vary with type of halogen. And when the halogen is fluorine, the relative rate is 312. When the halogen is chlorine, that's a reference. Relative rate is 1. The halogen is bromine, the rate is a bit slower. Okay. Then when halogen is iodine, the rate is even slower. Okay. This is a little bit different from the reaction rate. The how reaction rate depends on the halogen we have seen so far. In every reaction before this, okay, every reaction before this, when halogen is involved as a leaving group, almost always we saw iodide is most reactive, fluoride least reactive. In every reaction we have seen before this, okay, we talk about all the reactions we have seen organic 1, okay, when halogen atoms, they are leaving group, always, okay, iodide is most reactive, fluoride is least reactive, okay, because in every example we have seen organic 1, in those reactions, the breaking of carbon halogen bond is involved in the rate limiting step. And as we know, carbon iodine bond is the weakest, because this carbon iodine bond, this could be carbon bromine bond, this is carbon chlorine bond, this is carbon fluorine bond. Okay, your carbon fluorine bond is the shortest, the strongest, and the carbon iodine bond is the longest, the weakest. So breaking up carbon iodine bond is the easiest. Okay, so in all those examples, the carbon halogen bond cleavage is involving rate limit step. But here we see actually carbon fluorine, the fluoride is most reactive, iodide is the least reactive. So that immediately tells us that the carbon halogen bond cleavage is probably not involved in the rate limiting step. If carbon halogen bond cleavage is involved in rate limiting step, you should have seen that the iodide is most reactive. You see the logic here? If carbon halogen bond cleavage is involved in rate limiting step, you would have seen the iodide being most reactive, fluoride being least reactive. Okay, because you have observed other way around. So the logical conclusion is that the carbon halogen bond cleavage is not involved in the rate limiting step. Yeah, it will break at one moment, but not in the rate limiting step. So that's the key conclusion. Okay. So something else must be happening in the rate limiting step, the slow step. So what is the rate limiting step? Again, let's look at the rate law. So rate law is basically you see how the reaction rate depends on the concentrations of chemical species involved in the reaction. Okay? So from rate law, chemists have found that the rate of the nucleophilic aromatic substitution reaction is proportional to the concentration of alkyl halide and the concentration of nucleophile. Not alkyl halide, aromatic halide. Concentration of aromatic halide and the concentration of nucleophile. So this rate law could suggest that is SN2 reaction, because SN2 reaction can have same rate law, okay? The same rate law, okay? Same rate law. But there's other, the experiment evidence suggests that it's not SN2 reaction. SN2 reaction does not have intermediate. You directly go from the electrophile go to the product. You don't have intermediate. And the chemists did find there's an intermediate involved in this, the nucleophilic aromatic substitution reaction. So the rate limiting step actually is the nucleophilic addition from the nucleophile to the aromatic compound. Specifically, in the rate limiting step, the nucleophile attack the carbon that attached to the halogen. So what you see as shown here is basically this long tail attacks this electrophilic carbon, the carbon connected halogen, and then to maintain the octet, this pair of pi electrons must come to here, okay? And obviously, this is just one of the resonance forms, okay? Because you can move this pair of electrons around, okay? So let me just give you an example. We're gonna see, how this, the negative charge will be able to delocalize over multiple atoms. But anyway, if you look at this carbon anion, okay, this negative charge is next to a carbon that is this negative charged carbon is single bond to a double bonded carbon. So this is an allergic carbon anion, as we have seen in Organic 1, chapter 11. Okay? This is allergic carbon anion. Being allergic means that negative charge can be delocalized over other, the atoms. Okay, and obviously you see from here to here, the aromaticity of the ring is destroyed, is lost. Okay, so this step is largely endothermic. From here to here is largely endothermic. So based on the Hammond postulate, when you have a hugely endothermic step, likely you will be the rate limiting step, a slow step. So this is a rate limiting step. Okay. Now this is kind of sigma complex, but this is negative charged sigma complex. Okay. And then in the next step, the sigma complex loses the halide. Basically, this halide come to here, push the halide off, and obviously this step you restore the aromaticity, push the halide off. So this step is a highly exothermic step. So it's a fast step. It's not a rate limiting step. So this is important. Why the fluoride could be faster than iodide? Yeah, because of the carbon fluorine bond cleavage here will be slower than carbon iodide bond, but this step is not a rate limiting step. So what you can see, the carbon halogen bond cleavage is happened in a faster step, it's not a rate limiting. So although carbon fluorine bond will cleave slower than carbon iodine bond, but it's not really limiting, not impacting rate. Okay, so that's why fluorides could be more reactive than iodide. Okay. So the potential energy diagram of this reaction is kind of very, very similar to electrophilic aromatic substitution reaction. Is addition elimination mechanism. The first step is addition, second step is elimination. In the first step, the aromaticity is lost, so it's highly endothermic and rate limiting. Second step, you're going to restore aromaticity, so it's not rate limiting at all. So you have to focus on what happened in the first step to establish, how the structure of the aromatic compound affect its rate. So look at the first step. Okay. So basically, keep your attention on how the stability of this anionic species affect by the its structure, and because of the if particular structural factor makes this anion more stable, then its formation will become faster. So overall reaction will be faster. So basically, you have to pay close attention to the structure, stability of this guy. Now we can understand why having a very powerful electron withdrawing group can speed up such a reaction, because this intermediate is an ionic species, negative charge. So negative charge species, they will be stabilized by powerful electron withdrawing group, because electron withdrawing group help disperse negative charge towards the substituent. Like a nitro group, okay, is a very powerful electron withdrawing group, right? So it keeps electrons towards itself. And then if the nitro group pull the electrons away from the negative charges, like help it become more stable. Okay? Now, especially you see when the nitro group is the ortho or para to the fluorine. Okay, here is para. Okay, so now when the nucleophile attacks the electrophilic carbon connect to fluorine, the negative charge is here. Okay, then just draw all the resonance form out. So you can move this pair of electrons to here. Then this pair of electrons, okay, to maintain the octet, this pair of electrons has to move away. So you can first move to this carbon. Okay. Now that's important. You see now if the nitro group direct connect to this negative charge carbon, then this pair of electrons can move to here, then move all the way into nitro group. So when the nitro group is also or para to the halogen, the corresponding sigma complex, okay, can have the negative charge delocalize into the nitro group, and because nitro group is such a powerful electron withdrawing group, so the most stable state is that you have the negative charge delocalized into the nitro group. So this resonance form is actually the most stable of all forms we have seen here. Okay. And if you have the fluorine meta to the nitro group, now if you let the nucleophile attack the carbon connect to fluorine, the negative charge will be on the next carbon. And then you draw the resonance form again, you will see the negative charge will not be able to on the carbon directly attached to nitro group. So negative charge is actually here, okay, or here, but not here, okay. So that means the negative charge will not be directly delocalized into the nitro group. So you only can have these three resonance forms, okay. So that's why the meta, the nitro, let's say metafluoro nitrobenzene, okay, will be less reactive than ortho or para version. So here, this in the previous one, you actually can write another resonance forms. So which is if you look at this guy, you can totally have 4 resonance forms. You also can put the negative charge here, okay, and then here. So obviously, if you look at the importance of those resonance forms, those 3, okay, they of similar importance, but this guy is of higher importance than the rest of 3, because you have the negative charge going to the most electronegative oxygen atom. So certainly this is a most stable one. Okay, but you know you can write the full resonance form. Okay, so the you know for the sigma complex you will be getting from the you know the para or also fluoronitrobenzene, you can write the full resonance form, okay, and especially this resonance form, okay. But for meta, you know the fluoronitrobenzene, you only can write 3 resonance forms. So that means the sigma complex of the you know the meta fluoronitrobenzene is substantially less stable than the ortho or para fluoronitrobenzene. And as we know, the sigma complex formation here, from here to here, is rate limiting. So if the sigma complex is more stable, it forms faster, and overall reaction is faster. So that's why you will see the you know these 3 guys, okay, they have you know the different reactivities. So these 2 guys, okay, will be sizably faster than the meta version, okay, because of the sigma complex formed from these 2 guys, okay, will be more stable than the sigma complex formed from this guy. Okay, so these 2 guys will be you know, obviously most, you know, more reactive than this one, because these 2 guys, they can form more stable sigma complex. Therefore, the you know the sigma complex will form at a faster rate. Therefore, the overall reaction is you know faster. Now the question is about why you know the chloride are more stable than chloride. Again, we have to think about sigma complex. Okay? Just think about the you know the this one react with this, okay, or and this one just the chloride, okay. So the methoxide is nucleophile. So if it react with fluoride, it gives this sigma complex. React with chloride, it gives you right side sigma complex. So the argument is that you know again it's formation of sigma complex is rate limit. So we are comparing these 2 sigma complexes. So everything else is the same except that the fluorine is more electronegative than chlorine. So the fluorine as a more powerful, more electronegative element, so it can stabilize negative charge better by inductive effect, stronger inductive effect. So electron withdrawing group always stabilize negative charge. Fluorine is more electronegative than chlorine here, so it can stabilize negative charge better. So that makes this one more stable than this. And the sigma complex formation is rate limiting. So this one forms faster. Therefore, the nucleophilic substitution of this one is faster than this. So as you have seen that you know in the EAS reaction, the nitro group electrophilic aromatic substitution reaction. You know the reaction we have spent most of time on in chapter 13. Nitro group is a very powerful deactivating group. But here in nucleophilic reaction, nitro group now has become activating group because of the, you see here, more nitro group makes more reactive, right? So nitro group become activating. Okay? So really, the activating or deactivating for a given substituent, you have to look at what's the nature of the reaction. So if it's electrophilic reaction, the nitro group will be deactivating. If it's a nucleophilic reaction, nitro group will be activating. So it really depends on how the nitro group impact the the sigma complex stability. Because in an EAS reaction, the sigma complex is positive charge, so nitro group will destabilize. But in a nucleophilic aromatic substitution reaction, nitro group, the intermediate sigma complex negative charge, nitro group will stabilize. Okay? So in any case, nitro group electron withdrawing, very powerful electron withdrawing. So you really have to think about the nature of reaction before you apply the term activating or deactivating. Okay? So because of, see, in electrophilic aromatic substitution reaction, the P intermediate is positive charged. Okay, so nitro group destabilized. Okay, electron withdrawing nitro group destabilized. But in nucleophilic aromatic substitution, the key intermediate is negative charge, and the electron withdrawing nitro group stabilized. So obviously make it faster. And just a few more examples about the nucleophilic aromatic substitution reaction. So because the fluorine atom, they are is a single most electron withdrawing element. Okay? I'm not saying group, element. So polyfluorinated aromatic compound can undergo mono substitution very easily. One example is you have a hexafluorobenzene. If you treat with sodium methoxide, you can very easily have one of fluorine replaced by methoxide. Very high yield. Okay. Does anyone have an answer why it's much more difficult to install a second methoxy group? See, it's very easy to replace one fluorine with the methoxide ion, okay? But it's a lot more difficult if you want a methoxide ion replace another fluorine, doesn't matter which one, okay? A lot more difficult. Can anyone tell me why? It's much more difficult to have another fluorine replaced by methoxide. Much more difficult. First one is very easy, okay? Second one is a lot more difficult. Does not say you won't have it, but much more difficult. Basically, just to rephrase the question, okay, means this one can react with this easily, okay? But this compound, if you want to react with this one, much more difficult. Why? Think about it, okay? Alkoxy group, this group, in the early part of chapter 13, we treat it as what kind of group? It's electron donating or electron accepting. Overall. Well, and no volunteer, that's a call name. Okay. Let me see. Mr. Ben? Yes. Can you tell me the methoxy group is a electron withdrawing or electron donating group? When we discussed in when we talk about EAS reaction, we discussed the activating group, strongly activating group, those things, in the earlier part of chapter 30. And do you recall what's alkoxy group usually is what kind of group? You don't recall? Okay, that's fine. Just give you a hint, okay? Methoxy group. We have the lone pair here, okay? So check the notes earlier part. What's alkoxy group? What kind of group it is? Mr. Zaman? Huh? Donating. Okay, very good. It's donating. If it's because the oxygen lone pair, the resonance effect is electron donating. Okay, far more powerful than the inductive effect from oxygen. Resonance effect is stronger than the inductive for oxygen. Okay, so it's the electron donating group. Electron donating group will destabilize a nucleophilic aromatic substitution. It will slow down a nucleophilic aromatic substitution or activate a nucleophilic aromatic substitution. Activating or deactivating or nucleophilic reaction. Deactivating, okay, because of the nucleophilic aromatic substitution, they have a negative charge intermediate. If you have electron donating group, make it less stable. The electron donating group makes it slower. Okay, so because methoxy group is actually pretty good electron donating group, so it's actually a deactivating group for nucleophilic reaction. So that's why after install, one of them, this guy become less reactive than this one in a nucleophilic reaction. Okay. I think the last example is 2-chloropyridines undergo pretty fast nucleophilic substitution because of this pyridine. Okay, it's just like remember that in the EAS reaction we treat the pyridine similar as a nitrobenzene. Okay, so in nucleophilic reaction, similarly, you can treat, the 2-chloropyridine similar to 2-chloronitrobenzene. Okay, so that's why it can undergo nucleophilic reaction pretty easily. Okay, and again, you can look at why it can undergo nucleophilic reaction easily, because if the nucleophile attacks this carbon, you will get a sigma complex. And in one of the most important resonance form, the negative charge can be on nitrogen. And the nitrogen, as we know, it's more electronegative than carbon. So it's very happy to have that negative charge on nitrogen instead of carbon. Okay, so that's why this one is actually pretty reactive. If you have the 3-chloro, the pyridine will be substantially less reactive in a nucleophilic substitution reaction. Like this one, you will be substantially less reactive in nucleophilic, substitution reaction, because the negative charge will be on carbon instead of nitrogen atom. Okay. This will be less reactive. Then this. Or this. Para and nitro usually, para and ortho usually go together. Okay.